Okay, thank you very much for being here or attending this conference in presence way. As you can see, I am kind of the exiting generation, so I'm much more used to look at the people in the face rather than in a screen. And also, I am going to talk about a topic that probably most of you are not very much familiar with it, which is hydrogen-induced cracking, because this problem is very common when you, in the oil and gas industry that uses or processes sour hydrocarbons, which are hydrocarbons that contain hydrogen sulfide. And but I think the topic is interesting to show you a problem that has been in the field for many decades, but is not yet fully understood. This work is basically performed by my group of Pipeline Integrated Assessment Group. That's the name in English. And we also have a collaboration with the, I can never pronounce this name, Saskatchewan in Canada. When I went to visit them, the guy at the customs in the airport in Canada asked me where I was, what was my final destination in Canada, and I say Saskatchewan, and he told me, bless you. So it is always for him. Okay, let's talk a little bit of history. In the 1970s, with the development of the Trans-Alaskan pipeline that require high strength but low carbon and low alloy steel to be able to build this pipeline that had to endure temperatures below 50 degrees Celsius, below zero, and have to have a high weldability and high strength. A new generation of pipeline steels appeared. These steels gradually have been replacing the traditional ferrite and perlite steels with these typical elongated sulfide manganese non-metallic inclusions. And these new steels are basically high-strength low alloy. That means they have been treated with vanadium and calcium and some other rare earth elements to produce an ultra-fine grain microstructure, and also they modify the shape of the inclusions to be round ones, because in the first investigations of HIC, they realized that these elongated inclusions were the nuclei for this HIC. And the microstructure, well, it looks like quench and temper, but it's not quench and temper. It's it is produced by controlled rolling processes. They call it thermoforming. So that gives us, in addition to a very fine grained microstructure, also the reinforcing second phase is basically bainite and martensite. Well, the most widely accepted theory of HIC is the so-called pressure mechanism, where the corrosion reaction of the iron releases hydrogen, but then the sulfur prevents the hydrogen to combine and form hydrogen gas. So the hydrogen is absorbed by the hydrogen in so-called atomic state. We don't know what's the real state of this hydrogen, so we are just okay on calling it atomic hydrogen. Atomic hydrogen doesn't like to be in the atmosphere, so it diffuses very rapidly in matter of minutes into the metal. And once it is into the metal, it keeps diffusing inside until it reaches some suitable trapping site where it recombines back to hydrogen, where the fugacity of this reaction is about 1,000 to 3,000 atmospheres. So the pressure is very high, so it cracks the material. And then as the hydrogen accumulates in this cavity, the cracks keep growing, but they grow internally. And they just keep growing, and so they, at the end, make the plate to look like a sandwich. Sometimes they can go stepwise because of the interconnection of cracks being nucleated at different depths in the plate. And sometimes, in the presence of high normal stresses, the cracks can deflect and form stress-oriented cracks which are indeed very dangerous. Well, despite this knowledge that has been around for many years, there are several intriguing questions about this phenomenon. One of the probably most intriguing questions is, if these trapping sites are all over the microstructure, why some cracks nucleate rather easily, like this big crack that we can see here, and why some other cracks are very small? As we will see in the next slides, there is also a delay in the nucleation of cracks. Some cracks nucleate just as soon as the plate starts absorbing hydrogen, and some other cracks, they can take days or months to form. Why? We don't know yet. What we will try to find out in this research. To be able to reproduce the hydrogen-induced cracking in the laboratory, we use this very simple but effective system, which consists of connecting the plate as a cathode to a DC power source, and then we glue an acrylic cell to the side of in this case, the plate is cut from a pipeline, actually from a piece of pipeline. So we glue this acrylic plate in this side, which corresponds to the internal side, where this sour hydrocarbon that is being transported is in contact with the plate, to consider implicitly this superficial condition that in my question to Dr. Araujo, I mentioned. See, when we deal with corrosion and surface cracking problems, we always have to remember that this is a surface phenomenon. Okay, so in this setup, we put the specially formalized electrolyte. We use an inert, in this case, platinum cathode. And by means of ultrasonic mapping, we are able to record the location and the growth of these cracks. Well, my colleagues in Canada, they used also this technique called hydrogen microprinting, which allow us to see where is the hydrogen passing through in the microstructure. The principle is similar to the photography. They put a layer of silver bromide. So the silver bromide reacts with the hydrogen. The silver precipitates as form of tiny droplets, and the hydrogen and the bromide, they just go in the solution. Then by scanning electron microscopy with EDS, we are able to identify these tiny platinum drops, so we can see where the hydrogen is coming out of the plate. Okay, so we we wanted to examine what is the difference of behavior between the new generation steels, which are, I forgot to mention, they are also high strength, and the old generation steels, the ferrite perlite microstructure steels, which are they have a lower degree. So we can see that the chemical composition, as you can see, these particular alloying elements, vanadium, titanium, and niobium, as well as these are in higher quantity compared to the traditional formulation. And also we have inclusion control, which is reflected here as a lower content of phosphorus and sulfur. And also the grades are significantly higher. Here are the microstructures of the tested material. Again, as you can see, yeah, it is a very different microstructure. And back in 1993, I was a visiting researcher at the NKK facility in Fukuyama. I participated at that time, it's a very secret project to develop sulfur-resistant pipeline steels. I signed a confidentiality agreement that lasted 20 years, I mean, but we're in 2025, and that was in 1993. So now I'll talk about it. So what we were doing, though, in that lab in Fukuyama was to develop this microstructure, and my work was to determine if these kind of steels were more resistant to HIC. In those days, we said yes, but I must tell you the truth, we have some results because they have invested several tens of millions of dollars in the developing of this steel. So the company wouldn't admit that HIC was a possibility of these new generation steels, which are supposed to be HIC resistant. So I couldn't do any further investigation after those 20 years passed. And here is the result. Yeah, the new generation steels, they can have HIC. These are the mappings. As we can see, we have this delay nucleation. You can see this plate, this X56 steel started to crack in the first 24 hours. It had some very well-developed cracks. Each these small squares is 1 centimeter. So you can see in the X46 and X52 plates, we have very, very little HIC after 120 hours. And also, something very important is that the first HIC cracks, they try to follow the shape of the inclusion they were nucleated in, which is elongated sulfide manganese inclusion. So these cracks are elongated. Actually, they are elongated in the rolling direction, which is the direction in which the non-metallic inclusions are oriented. And also, we observed that the HIC occurs in 2 stages. The first stage is the nucleation of individual cracks, and the second stage is the, I said it right. First stage, growth of individual cracks. Second stage, interconnection of cracks. But something very interesting is going to happen with the kinetics. Here is the new generation steels. Again, coupled steels started nucleating cracks in the first 24 hours. We observe delayed nucleation, not as delayed as in the other steels, but still it took 24 hours to develop the first cracks in this X80 steel. And the difference, the main difference is that the majority of the cracks have this elliptical, well, my students, they draw these crack locations as a square, but they are not square. They are like elliptical. And again, we observe the same individual growth stage and the interconnection stage. Now, here's the kinetics, and here's where the surprises begin. Because in the traditional fracture mechanics analysis, one of the most important commandments in our religion is that the cracks grow faster as they are larger, because the stress intensity factor is larger. You know, that's the first commandment, or the second commandment of fracture mechanics, religion. But HIC just doesn't follow that. I have presented these graphs since like 20 years ago, and in every conference there is always that says that my results are wrong because the cracks cannot deaccelerate as they grow. But in a conference, the same conference in Vicenza, Professor Paul Paris was in the room. There was a big debate about the accuracy of the results, and Professor Paul Paris do me the big favor that say, well, if it is an experimental result, it must be true. So it is true. Okay, I have just 1 minute left, so I'm going to rush. Okay, we measure the crack growth rate in the individual stage, and you can see it's much faster than in the interconnection growth. But if we overlap these two graphs, we are going to see that the new generation and old generation in the individual growth stage, they have very much the same behavior. The only difference is in the final total cracked area. So we try to correlate this with the diffusion parameters, and as you can see, with respect to the hydrogen solubility, we don't have a good correlation, but if we measure the density of irreversible hydrogen traps, we have a good correlation. But if we separate this data by microstructure, then the correlation is way much better. So this is telling us that hydrogen-induced cracking has to do with the microstructure rather than with the, well, some microstructure fracture. I'm going to skip this. This is the measurement of the corrosion rate. I'm just going to say that corrosion behavior is very much similar. Crack growth mechanism is virtually the same in both steels. And in the microprint technique, we observed that in the old generation steels, the hydrogen tends to diffuse preferentially through the perlite colonies, while in the new generation, the hydrogen permeates preferentially around the known metallic inclusions, which, remember, they were especially treated to become spheres or spinal shapes. We did also some EBSD, and we try to relate the crack growth rate in the individual growth stage with the grain misorientation angle. Again, no correlation, very bad correlation if we take the bulk data. But if we separate the data by by microstructure, old generation and new generation, then we see a big difference. So in conclusion, we can say that both old generation and new generation pipeline steels are susceptible to HAC. HAC occurs by the pressure mechanism in both steel types. The morphology of HAC is different, but the microstructure and mechanical strength do not have an apparent effect on the kinetics. But the microstructure affects the diffusion parameters, and this seems to be the controlling factor. Again, we didn't see any corrosion effect of the corrosion rate. So the big conclusion is that the kinetics of HAC depends on the synergistic interaction of microstructural parameters such as grain, boundary misfit, inclusion type, second phase time, type and content, and etc. And I probably have to learn some neural networks to analyze that, but that's something I will pass to my students. I am too old, I want to retire. Thank you very, very much.